Hey class, Adam Ward here. I want to look at a problem tonight that is adapted from 5.29 in the Mines textbook, where we'll take a look at CSTRs and plug flow reactors. So the setup of the design is here. In this problem we've got a influent with a concentration of 100 milligrams per liter, and our goal is to reduce that down to 15 milligrams per liter in a reactor. There's some information about batch reactor experiment given, that it takes 30 hours for the reaction to achieve this in a benchtop batch reactor study. And so our goal here is to determine what volume of reactor does it take for these. So we've got a couple of options, plug flow reactor, mixed flow reactor, and then a couple of CSTRs in series. So 3 tanks or 10 tanks in a row. From the given information about a batch reactor, you should be able to make your way to a first order rate coefficient of about 1.51 per day. Applying the design equations we've looked at for plug flow and complete mix reactors or CSTRs, we should be able to get volumes of 24,000 and 71,000 respectively, approximately, rounded to the nearest thousand. What I'd like to take a look at in this video is really what happens with these CSTRs in series. That's something we haven't covered yet. So to tackle that, let's start with our mass balance for a single CSTR. In this case, our accumulation rate is equal to the load, Q in, C in, minus the outflows, minus removals by that reactivity. And we're going to solve this as a steady state problem, so we can zero out the left-hand side. And through algebra, we can rearrange to get this equation in the top right of the slide. The outflowing concentration C is equal to the inflowing concentration C in, multiplied by the quantity Q divided by Q plus KV. So that's just an algebraic manipulation of what's written on the left-hand side. So what we've done so far is we've got this inflow coming from the factory at 100 milligrams per liter, and we had 5 million gallons per day coming in. And we've derived an equation here in a generic sense that will tell us about the outflowing concentration. Now what if that flows immediately into a second CSTR, drawn here in red and labeled C2? Well, if you knew what was flowing into it, C1, you could use that exact same equation to describe it. Now, what is a special case that we can look at here is how we could factor this all together. And so rather than, let me highlight in orange what I've done here. Rather than having C1 in that location, I'm just replacing it with its definition, and that comes from the previous equation. Now you might notice those two groupings in parentheses look the same, and as long as the volumes are going to be identical, we could generalize this. So for n CSTRs in a row, we could take the inflowing concentration times that quantity in the parentheses raised to the nth power. And this is a special case. This only works if they're going to be identical. So all of the volumes will be the same. If you had a small tank followed by a large, followed by a tiny, this doesn't work, and you'd have to go through them one by one. But for our case of identical CSTRs, this works. And so we can go ahead and apply that equation. If we solve it with an n equals 3, you should get a volume of 11,000 cubic meters. And to remind you, that means each of them has a volume of 11,000 cubic meters. Or in other words, you need 33,000 cubic meters total, multiplying by 3 because that was 3 CSTRs in series. And we can work through the exact same calculation for 10 in series. If you have 10 CSTRs in series and they're all going to be identical, each one is about 2,600 cubic meters, and you get 26,000 cubic meters total. And you'll remember for our single CSTR, we were at about 71,000, and for a plug flow reactor, about 24. And you'll notice what I've written there in orange, meaning as n approaches infinity. So as this becomes a series of infinitely small CSTRs lined up back to back, your answer will converge down to a plug flow reactor. In other words, the way we're treating a plug flow reactor is as a whole, as basically an infinite series of CSTRs. The last thing I want to do is look at what happens if these conditions are not ideal. So what happens if you accidentally have a concentration 10% more as your input? In other words, the exact same workflow, but let's start with an inflowing concentration of 110 instead of 100. So this is the case where someone makes a mistake in the plant and the effluent contains more of this compound than you expected. We can use our exact same workflow for the plug flow reactor problem. And what we find is we would be exceeding our goal of 15 grams per cubic meter at the outflow. We would be at 16.7. And reminding you, we were at 15 for our design condition of 100. Similarly, we can solve this problem for a single CSTR, and we're putting in the volume of that single CSTR of about 71,000 cubic meters. And what we find is the outflow is about 16.5. Again, that's in comparison to 15 for our design purposes. And n equals 3 and n equals 10 would exist somewhere in between those two end members. So what we're seeing here is that although the performance might be really different, although the volumes might be really different, the performance is pretty similar. In a plug flow reactor, that concentration remains just slightly higher because as that plug is moving along through the reactor, it's not mixing with anything else. Whereas in the CSTR, you've got this larger volume that's helping to somewhat dilute the added mass that you would have had coming in. You're getting some longer time scales in there that'll lead to more removal. So as a general rule, accidents in plug flow reactors are going to be a bit worse than in CSTRs. Because if you spill into that plug flow reactor, or if you put in some high concentration, it doesn't have anything to mix with. It's going to still have that defined period of 30 hours, and you're guaranteed to exceed your goals. The larger volume of CSTRs may buffer those extremes to some degree. So that's one of the key differences between CSTRs and plug flow reactors, and we'll look at more of these in class together. All right, folks, that's what I've got for you. Thanks for sticking with me, and I will see you in our next lecture.